how we can actually formally do this things. Let's say we want to now go for a parameterized surfaces, right? We want to parameterize our regions or curves, whatever we have. So the first example is actually associated with the line integrals. So this is a parameterized example where the surface or curves are just parameterized with respect to some parameters and stuff like that. So the first thing is an example of a line integral. So our differential forms or the integration of differential forms had this kind of form dx1 dx2 dot 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 raised with dx of n, and in short we can write it like this: sum alpha. This is some form, okay? And the right hand side of equation 2 that we discussed a little bit earlier would be written like this: t star phi inverse 1 dot alpha, like this, okay? So in this example we are going to integrate a one form along some curve. So let's say we want to integrate y squared dx plus x dy. This is our one form and we want to integrate it on a curve, a parameterized curve, on a parameterized curve. So let's say the curve is parameterized as follows: phi inverse of t. We have this x of t and y of t, because since this is a curve on a 2D space, and that's why it will have two components, x and y. You can also induce more components like z, w, and whatever, but the procedure is the same. And let's say this curve is parameterized like this: 5t minus 3, 5t minus 3. Okay, and let's not take this as 3, let's take it as 5. Now first things first, since we are dealing with a parameterized curve now, our goal should be to change the coordinates and bring the whole integral, that means the integral over this guy over here, in terms of t. That should be our goal. So that's why what we want to do is that we want to first compute the pullback mapping. That means this t phi inverse 1 or t star phi inverse 1, whatever. And this is pretty easy, you already know what it is. This is just this partial derivatives on the column matrices, and this is just 5 times 5, because you are dealing with a form and form will eventually act on vectors. So that's why you need to have this pullback vector or pullback mapping. Now what you do, since this is done, we note that our f of t, note that this is some f of xy, right? This is some f of xy, but we want to go for f of t because we want to get rid of these x and y's, and we want to express the whole thing as a function of t, that is the function of the parameter. So this f of t can be written as the following. Let's say f of t dt, which is a one form, and it will, let's say, take a vector which is a 1 cross 1, one row and one column vector. This can be written as this. That means f of t can be written as this guy. But this dt of 1, or this quantity over here, can be written as a t star phi inverse 1 y squared dx plus x dy. That means the initial function that we were working with. times 1. Then from here, what we can do is that we can write it as y squared dx plus x dy, and this mapping will go over here and it will act as d phi inverse 1 of 1, which should give me the following column vector. And this is a linear multiplication, so you just multiply the column vectors. This dx is a form and it will act on this column vector. Similarly, x dy, this dy is a form, this will act on this column vector, and you already know how to compute this thing, how one forms act. Dx will just take the first component and dy will take the second component. So this is just 5y squared plus x times 5, right? And now what we can do is that we can use the parameterizations that were given in the first place, that is x equals to 5t minus 5 and y equals to 5t minus 3. So now we use this x equals to 5t minus 5 and y equals to 5t minus 3. If you do that, the final expression will be something like this: 125t squared minus t plus 20, right? And now we finally have to integrate this thing. So we say, let's say our parameter varies from 0 to 1. This is how the limit is been set, let's say, and we want to compute this phi of c, and this c here actually means a line integral. So this t star phi inverse 1 alpha is nothing but an integral from 0 to 1 of this quantity over here, 125t squared minus 125t plus 20 dt. And this is a simple integral, and you can evaluate to know that the answer is just minus 5 by 6. Now you might ask, okay, I get everything, but what are we doing over here? Why is this 1 over here, and why is this d phi inverse 1 is giving me a 5 5 or a column matrix, right? So let's try to justify this as the following way. We already computed that this d phi inverse 1 thing is just a 5 by 5, right? And by doing this, we have induced the tangent and cotangent mapping. What it means is that, so this is a justification, is that when you do this d phi inverse 1, it's dx dt dy dt, you write it as 5 by 5 using the parameterizations. By doing this, we introduced tangent and cotangent mappings as follows. So this one, which belongs to the tangent space of the manifold, will become something like this, equals to 5 5 times 1, because now you are just using the value of this d phi inverse 1, and this is just 5 5, which belongs to d phi inverse 1 of p into r square. This is the justification. So what is the summary? How do you approach it? So the summary for this is that, at least for parameterized surfaces, first you find whatever is given inside the integral sign, that means if this is your quantity of interest, you find this f in terms of the parameter. Second, you compute the pullback mapping of the forms with respect to the parameter, because that's how pullback works. Third, you see the limits or find out the limits of the parameter. Then you just integrate it. And in fact, if you can just define your whole problem using a single parameter, your n-dimensional problem can be reduced to a just one-dimensional problem, and so on. So let us end by seeing another example, and this time we're going to not deal with line integrals, but rather what we're going to do is that we're going to take an example of a surface integral. Okay, so this is a surface integral example. So that you can get a better feel of how to compute this pullback maps and so on. So what we're going to do is that we're going to integrate this z square dx wedged with dy over the top half of the unit sphere. We want to integrate it over the top half of the unit sphere. So this top half of the unit sphere, this is our region. Okay, and the best way to do is to just go to the parameterization of r and theta for this case. So I'm giving you the parameterization over here, and this parameterization is given by r and theta. Notice that I'm using this phi inverse one because the x, y, and z goes inside phi and then pops out this r, theta, and whatever. And so that's why I use this phi inverse one on r and theta, that is the parameters, and I get these x, y's, and z's. So my goal is to write x in terms of r and theta, y in terms of r and theta, and z in terms of r and theta. Okay, so this is just x equals to r cosine theta, y equals to r sine theta, and z is just square root of 1 minus r square. And how does this z come? Well, the unit sphere will have an equation like this, where x square and y square, if you add them up, this is just r square plus z square. And since I'm talking about the top half, I will only take the positive square root of z. The negative square root would give you the bottom half of the unit sphere. So that's why I wrote it as a square root of 1 minus r squared. Now we are done. Now we have to compute the pullback, right? This t phi inverse one thing, whatever that is you want to call it. And this is just dx. We have two parameters, r and theta. Sorry, it's a phi, it should be theta. And all of this is coming from the definition of the pullback that we started earlier. So if you're confused, I suggest you to look at it once more. and finally you have dz, dr, dz, d theta. And this is just given by, you just take the derivatives. The first one is just cosine theta, the second one is minus r sine theta, then it's the sine theta, and this one would be a r cosine theta. Then you have dz by dr is just minus r divided by square root of 1 minus r squared, and the theta parameter doesn't appear here, so it's a 0. Okay, and now what you want to do, you want to put the final piece of the puzzle, that is, let's say this is our g of xy, for example, or g, and we want to compute it in terms of r and theta because we are parameterizing our problem in that way. And what we do is that we want to finally use the fact that this g of r theta wedged with, let's say, dr wedged with d theta, and if you introduce two column vectors like this, it will actually give you g of r theta, right? This is pretty easy to see because these guys, that means the forms with these column vectors, will give you a determinant, and therefore we can write this g of r theta as g r theta dr wedged with d theta. Again, introduce those column vectors, and on the next line what you want to do, you want to introduce that map t star phi inverse 1 z squared dx wedged with dy, and there are this t star phi inverse 1 1 0 0 1, sorry, it shouldn't be here. On the next line you just put z squared dx wedged with dy, and you have now t phi inverse 1 1 0 t phi inverse 1 0 1. Now you put the values of t phi inverse 1 that you found earlier and you multiply them with this column vectors, and note that the reason we are introducing two column vectors is that we have a 2 form. In the previous problem we had a 1 form, so we just introduced something like this, a box that contains a 1. That means it's just a 1 times 1 matrix, or just a column matrix with a single entity. And this time we have 2 forms, r and theta, so we need 2 vectors. Okay, that's why we are doing this whole thing. So if you use the value of t phi inverse 1 that you computed here and you multiply them with these column vectors, this will become dx wedged with dy. Then this will give you a cosine theta sine theta minus r square root over 1 minus r squared, and you have minus r sine theta r cosine theta 0. Now it's pretty simple. You have 2 vectors, you have 2 forms. You just take for dx, this will just eat the first quantity over here, dy will eat the second quantity over here, right? That's what you think, but this is actually a determinant. So the determinant will only consist of these 2 parts because there is no third form over here like dz. If it had a dz, it would be a 3 by 3 thing. So this dx dy will act on these 2 vectors, and it should give you something like this, a determinant cosine theta minus r sine theta, then sine theta r cosine theta, and this is just z square. If you compute the determinant, this is just r. Then what you do, you express z in terms of r, and z square is just 1 minus r square times r, this is just r minus r cube, right? And we are almost done. Okay, why is it not? It's not. Yeah. So finally, what we can write is that finally t star phi inverse 1 acting on z squared dx wedged with dy will just give me r minus r cube wedged with dr wedged with d theta. Now we can use that equivalence that we used earlier. This will be equivalent to obviously the integral, not the quantity. The integral will be equivalent to r minus r cube dr d theta. Now we have to find the limits. Well, this is a unit sphere, so r will vary from 0 to 1 and the theta will vary from 0 to 2 pi. So 0 to 2 pi, this is the theta integration and this is the r integration, and you can see that these two values separate very well. So r minus r cube dr will have a 2 pi from here, and r minus r cube integrated from 0 to 1 will just give you what? A 1 by 4, and this is just pi by 2. This is your answer. So a seemingly difficult integral can be put to much simpler notation, even though a little bit of long computation, with the help of differential forms. And this is how you actually work around with differential forms and their integration. And this is the last lecture, and thank you.